Let's look at the prototypical example of a quotient space construction, which will really sort of make things concrete for you, I hope. So take the vector space to be just good old R3, and let U be the z-axis, so the third coordinate. Okay. Then for any elements A, B, and C, sorry, A, B, C, and alpha, beta, gamma of R3, ABC plus U is going to be the same as alpha, beta, gamma plus U. So we have two equivalent coordinate triples. If and only if their difference is an element of U, which means it's going to look something like that, right? And then this is going to be true if and only if A equals alpha and B equals beta, and then there's no condition on the third coordinate because we can sort of take up the slack with the 0, 0 lambda term for anything else. So in essence, we are ignoring the z coordinate, right? And that's what we picked for our u. And what we picked for our u is the stuff that we don't care about. Okay, so these two things are equal up to an element of u. So now let's consider the xy plane. So this is going to be all the points of, or all the elements of R3 where c equals 0. Okay, so then this guy is going to be the range of a linear transformation the operator on R3, which is projection to the xy plane. So we just kill the third coordinate. So in your previous linear algebra class, you probably saw that there's different sorts of geometric transformations associated with matrix multiplication, and the basic types of transformations you can have are rotations, reflections, shears, scaling, and projection. And of those, the only one that's not invertible is projection. Okay, so note the distinction here. So I'm trying to distinguish between the quotient map pi and the projection map t. So note that pi is not an operator on R3 like t is. Pi is a linear map from R3 to R3 mod u. Yeah. And if we look at pi of A, B, C, it would be A, B, C plus u. And so these are just different types of things. Yeah. On the left, we have a coordinate in R3. On the right, we have a parallel affine subspace. So what we see is that V is actually the orthogonal direct sum, or sorry, V is the direct sum between U and Z. And if we do V modulo U, we get something that is isomorphic to Z. And so this and this is the main point. So it's isomorphic by specifically the map that sends ABC plus U to AB0. Okay, and let me pull in a picture here. Ooh, that came in rather large. And so here's the idea, and we've got T is an operator acting on this space. So if you have a vector space and you identify a subspace of it, like in this case, our the null space of T, then you can say, oh, I wonder if V is actually the direct sum of this space U with some other thing Z. How can I figure out what Z looks like? And then what this is telling you is that the quotient construction tells you how to find out what Z looks like. And then so keep this example in mind when we talk about the induced map in the next clip.